Can you hear my voice?
Yes, sir.
Okay, great. Okay, recording started. Yeah, great. So, so we have been discussing carbon nanotube. Carbon nanotube is a kind of a nanostructure which is basically a tube-like structure, as I mentioned yesterday. So you have a, so this is like a graphene sheet. Okay, you see hexagonal structure. Okay, of each corner contains carbon. Okay, and if you manage to roll this sheet and form a tube, it will be your nanotube. Okay, it's like a kind of 1D structure. Whereas I mentioned if you can form roll this structure and form a buckyball kind of structure, it's then fullerene. And these sheet, if these sheets are multiple in number, okay, with having van der Waals force uh, among them, okay, so they are then graphite, right? Now this carbon nanotube is very important because it has lots of unique properties which is better than that of silicon. Okay, so when first time people managed to develop carbon nanotube, there have been lot of hypes to make FET out of it, and what are the other applications possible, and so on and so forth. So I mentioned nanotubes are two types. Carbon nanotubes are two types. Okay, multi-wall carbon nanotube known as MWNT, where multiple rolled layers are there of graphite, whereas single wall carbon nanotube SWNT, so it is like one atomic layer, thick layer of graphite. Okay, so here diameter is a few nanometer, right? Where here the diameter is like few tenths of nanometer. Now, as I said, like it has a lot of unique properties. One of the important properties, high aspect ratio structure. Okay, so very tiny diameter but long. Okay, so high aspect ratio structure, high mechanical strength because it is it has sp2 hybridization, so it has high mechanical strength. Okay, pretty good Young's modulus and all that. It has very high electrical conductivity. Okay, and I mean, when the electrons flow through carbon nanotube, it hardly scattered, so it gives you elastic transport. So the devices, if you can make in carbon nanotube using carbon nanotube, devices will be fast, much faster than that of silicon. Okay, it has high thermal conductivity, so it will dissipate heat very quickly. And it can carry quite a lot of current. Okay, single wall carbon nanotube can be metallic or semiconducting. Usually the multi-wall carbon nanotubes are definitely semiconducting, but single wall can be metallic or can be semiconducting. Okay, it is chemically inert, so that's also very good. Okay, so not attacked by strong acids or alkalis and so on. And nanotubes can exhibit high surface area, right? High surface area it can exhibit. So if you have like some surface phenomena, it will be very good. For example, if you go for sensing, it has lots of surface area which might help in sensing and all that, right? So these are some key important aspects which motivated researchers over the years to make carbon nanotube based devices. I showed this slide yesterday, so you can roll carbon nanotube in different way, different orientation. There is a in and M index. I just don't want to go into the what is N, what is M, but if you roll differently, the property will be different from the nanotube, and it has different names. For example, zigzag, chiral, armchair, depending on how you are arranging, how you are rolling that graphene sheet, and came up with the carbon nanotube, right? So this is armchair, this is chiral, this is zigzag, and so on and so forth, right? Now, again, this slide I have shown yesterday. Just keep this for the moment. Now the thing is, we did mention a couple of synthesis technique, that is the fabrication technique. One of the fabrication technique was arc discharge technique. This was the first technique through which carbon nanotube was made by Ijima. There is a sealed chamber, graphite electrode, okay, and you apply voltage, and you apply you give low pressure, and you give high voltage, so high electric field will create electrical discharge, DC arc, okay, and it was found that basically forms shoots on the electrode, and those nothing but carbon nanotube. So I've jot down the process, about the process, so you can go through it and learn more about this particular process. For example, DC arc can also be carried out using argon, CH4. In fact, CH4 is best among the three gases, okay, methane, for growing carbon nanotube in this particular case, okay. Usually the yield is not much for this particular process, but the mass production first time demonstrated by Ojoy and Ibsen around 1993 or so, right? So this this is the first demonstration of carbon nanotube, and this is using arc discharge technique. Just keeping this part so you can control the pressure and can develop different kinds of allotropes of carbon using this particular equipment, okay. Then I talked about yesterday laser ablation technique. Again, this is not a very high yield process, but you can have like much high quality CNTs, because it is a very high temperature process, okay, around 1200 degrees centigrade. You put it inside an oven, this jacket, and you have a laser, okay, and you bombard graphite target with the laser. So here again I have described the method, okay. So in laser ablation, as I said, a pulse laser vaporizes a graphite target in a high temperature reactor, while an inert gas is bled into the chamber. So here, for example, you can use argon gas, which will take this graphite, okay, which is come out because of this laser bombardment, and you take this argon gas, acts as a carrier gas, and take this graphite particle, okay, and that will basically when accumulate on the copper, water cooled copper, okay. So here you see nanotube developed on the cooler surface of the reactor, so this particular process, as I said, is very high quality CNTs. However, it is more expensive. Compared to arc discharge technique, because you need laser, you need very high temperature, and so on and so forth, okay. Now this was first developed by Dr. Richard Smelly and his co-workers in the Rice University, US. So this is another technique which is very popular technique and very widely used. This is known as chemical vapor deposition technique, or CVD technique. In this particular technique, you use as I told you in the last class, that this is whatever carbon nanotube you buy commercially, mostly made with CVD, because you can have you can grow quite a lot, and I mean the yield is quite a lot in this particular process, okay. Here you use ammonia, nitrogen or hydrogen, okay, process gas, a carbon containing gas, okay, such as acetylene, ethylene, ethanol or methane, okay. In this case here I've shown you C2H2. So this will basically dissociate when you go inside the chamber. This gas, this carbon containing gas will basically dissociate, okay, and the nanotubes will grow at the sides of the metal catalyst. So you have a substrate, you basically coat the substrate with metal catalyst, okay, and this metal catalyst, then you heat it up, so it will form small islands, and basically carbons, dissociated carbon push those metal particle and forms carbon nanotube under these small metal islands, okay. um, as I said, CVD is a common method for commercial production of carbon nanotubes. So during CVD, as I said, a substrate is prepared with a layer of metal catalyst, most commonly nickel, cobalt, iron, or a combination. The catalyst film is heated up to form small islands, and the diameter of the nanotube basically governed by this the island size, okay. So a lot of effort being there to optimize this process. How thick will be this metal catalyst, what temperature you use, and so on and so forth. What catalyst you use, whether the combination or a single catalyst, and so on and so forth. And to initiate the growth of the nanotube, two gases are flown inside the reactor: a process gas such as ammonia, nitrogen, or hydrogen. Here I have written ammonia, okay. So a process gas, and a carbon containing gas such as acetylene, ethylene, ethanol, methane, and so on. So one of these gases and one of these gases. Now nanotubes grow at the sides of the metal catalyst, and the carbon containing gas is broken apart at the surface of the catalyst particle, and the carbon is transported to the edges of the particle, that is the catalyst particle, where it forms the nanotube. The catalyst particles can stay at the tips. As I said yesterday, the catalyst particles can stay at the tips. You can remove if you want, or you can keep it on the tip of the carbon nanotube. Okay, so as I said, CVD can give you very high yield CNTs and useful for commercial purposes. Now, here is a demonstration which I have already showed you. So told you. So substrate, you catalyst, you heat it up, it forms a small islands. Put in the CVD chamber, it will give you around 600 to 800 degrees centigrade. It will give you carbon nanotube. So these are like catalyst clusters. So small, you see small catalyst islands, okay, and these small catalyst island. So this is the side view. You see the small catalyst islands, and they will basically give you carbon nanotube. So this is the image of using ACM, scanning electron microscope image, which we will study later on. And you see in the tips are shiny, so there are metal nanoparticles on the top of the nanotube. Here we have used like C2H2 and ammonia, around 600 volt. The growth time was around 15 minutes. Okay, so this is your carbon nanotube using CVD chamber. Okay, grown in CVD chamber. Another technique I mentioned yesterday was PECVD, plasma enhanced chemical vapor deposition. Okay, plasma enhanced chemical vapor deposition technique. So here, instead of high temperature, what we use plasma, so that the carbon containing gas dissociates. Okay, so it's the same purpose. Here we use temperature, here we use high temperature. Okay, but to dissociate this carbon containing gas, whereas here we use in the PECVD we use plasma to dissociate the hydrocarbon, that is the carbon containing gas. Okay, and as I said, instead of using high temperature, we use plasma. It is possible to get vertically aligned tube in this particular case because you use high electric field. Okay, this plasma. However, one might get defects in the carbon nanotube because it is not a high temperature process, because high temperature process often reduces the defects. Okay. So, and also sputtering environment. So this is another technique. And this slide also I showed you in the last class. This is just a tabular form of whatever I have discussed so far. Now, I also mentioned this, so that skip this part. So what I did tell yesterday is like you have so many parameters, you can control those parameters, optimize those parameters according to your need, so that you come up with a carbon nanotube which is specific for your application. Okay. Now, here we stopped, I think, in the last class. We mentioned that carbon nanotube can be made for, can be used for, I mean, at initial days, the only idea we had, like, we have to make CNT based FET, like, because that time with silicon we are struggling, we have a lot of challenges, like as I mentioned in IC roadmap, there are a lot of challenges with silicon based MOSFET, and then we had like breakthroughs to overcome those challenges, like high K dielectric, restrained silicon, and so on and so forth, right? Lowly doped drain, and so on. So people then looked for like alternate material, and one of the material was carbon nanotube, because it has so many good properties. One of the properties is it has ballistic transport, so it gives you very high mobility, right? So one of the way people fast demonstration of carbon nanotube based came from Delft University. Okay, group from Delft University, Holland, 1998. If you are interested, you can go through this particular paper to more about this device. Okay, how fabrication is done and all that, how is the characterization, and everything you will get in this particular paper. It was published in Nature 1998 in the month of May, right? So it is first demonstration of carbon nanotube based MOSFET, carbon nanotube based FET from Delft University. So if you look at the structure, it is a silicon substrate. On top of silicon substrate, you have grown SiO2, silicon dioxide, right? You have then you have spin coat CNT. So you grow CNTs for one of using one of these technique. Okay, using one of this technique, you grow CNT, and you disperse CNT. Disperse means you make a homogeneous solution of carbon nanotube in a liquid. Okay, so you can't make a carbon nanotube is not soluble, but what you can do, you can disperse. Okay, so you can mix the carbon nanotube in a solution. There are many solutions, like NMP is one of a solution, DMF is another solution, and so on and so forth. So these kind of solutions you can use to make a carbon nanotube solution, and then you drop cast, that is put a drop of carbon nanotube on a silicon substrate or silicon wafer, then you spin coat it, you rotate it. Okay, and then the carbon nanotube will spread around the substrate, and you you put metal contacts. Okay, for example, here they have done with platinum. Okay, you can have like a single carbon nanotube, you can have like multiple bunch of carbon nanotubes, because it is not easy to have a single carbon nanotube and just deposit metal contacts on that nanotube. It's not easy, it can be done. So this is backgated CNTFET. Why it is backgated CNTFET? Because this silicon is sorry, so this silicon acts as a gate. Okay, it is usually like highly doped silicon, right? Highly doped silicon, it acts as a gate, and this is my gate oxide, and this is the nanotube which acts as a channel, right? So it acts as a channel. This is my source and drain, right? And this is my back gate. So from back side, you are controlling the current through the FET, CNT based FET. You see, it is a very simple structure, nothing complicated, very simple structure. However, there are issues. What are the issues? Issues are like you can't have like multiple gate on the same substrate, because you see your substrate is acting as a gate, right? So you can't have like more than one FET, because then gate will be common, right? But the advantage is a very simple structure. So one drawback is you can't have like multiple FET. There is from the same substrate. There is another drawback, which is like your threshold voltage is very high, because you see usually the substrate thickness is quite a lot, right? Substrate is usually thicker, several hundreds of micrometer. It's not like a few nanometer gate, right? So it's like several hundreds of micrometer silicon wafer thickness, and on top of that you are going SiO2. So you need high voltage. You have to apply high voltage at the here at silicon, right? So these are some of the drawbacks and some of the advantages, right? So this is backgated CNTFET. This is the first demonstration of CNTFET in 1998 from Delft University. This top-gated CNTFET. Top-gated CNTFET is more like conventional FET, right? So we have a silicon, okay? It doesn't has to be highly doped silicon, although it is shown highly doped, but it doesn't has to be highly doped silicon, okay? Silicon, there is SiO2, and again you can grow carbon nanotube, you can spin coat carbon nanotube, okay? And then what you do, you deposit oxide on the carbon nanotube, and then you deposit metal. Okay, you deposit oxide and then you deposit metal. So it's like a conventional FET structure. Okay, so metal, oxide, and then channel, and then there is source and drain, another metal contacts. So this is like a more conventional FET structure. It is first demonstrated in the year 2002. Here is the paper, APL. It was published in APL, Applied Physics Letter. Again, if you are interested, you can see this paper. It is first developed in IBM, TJ Watson Research Center in US. Now the advantage here is, you see the gate oxide thickness is very tiny, so you can get away with applying a small gate voltage, right? You can have multiple FET here because the substrate is not your gate, so you can have multiple FET on the same substrate. So, but the thing is, here the process is little bit more complicated. Here you see you have to grow oxide or deposit oxide on top of carbon nanotube, okay, which is not the case here. It is not the case here. It is more easier to grow oxide on silicon rather than deposit oxide on carbon nanotube, right? So in a way, this is a little bit more complex process compared to the backgated CNTFET, but you can apply lower voltage, smaller amount of voltage at the gate. You can have multiple FET on the same substrate, and so on and so forth, right? So this is top-gated CNTFET. Wrap around gate CNTFET. You remember in FinFET, while we are discussing FinFET, we talk about like if we have like a gate all around the channel, it will be excellent, right? It will be excellent. Then we have like more control from the gate and so on and so forth. So people actually demonstrated, in fact, from the same research center, IBM, TJ Watson Research Center, in collaboration with Harvard University and Purdue University, they demonstrated that that carbon nanotube, here is a carbon nanotube, and they grow oxide around the carbon nanotube, okay, made with Al2O3. So they grow oxide around the carbon nanotube. Then what they did, they remove oxide from the sides, okay, and then they deposit metal. So here is just a schematic. You deposit metal, you remove oxide from these portions of the carbon nanotube, right? So you see you have like an excellent gate control, okay. Again, this is done on the silicon substrate. On top of silicon substrate, you grow SiO2, and the entire substrate is entire FET is on this SiO2 substrate, right? And this the carbon nanotube, you see its performance is much better compared to backgated CNTFET, top-gated CNTFET. But the problem is it's way more complicated to make this. way more complicated. It's hell of a job to create oxide around the carbon nanotube, and then you etch it out. Okay, if you want, you can dope it. For example, they dope make it p type. Okay, so it's up to you. If you need, you dope it, right? So it's very complicated process, but people have demonstrated that you can have like a wrap around get CNTFET. Okay, and it performed quite well. Now there are other CNTFET, for example, suspended CNTFET. Suspended CNTFET is like CNTs. Your CNTs are suspended between source and drain. Okay, and here you see air. Air is there, right? Air, and this is your gate, right? So one of the advantage of such a FET is like the mobility is even higher, because here this CNT is not in touch with your substrate. In earlier cases, the CNT is in touch with your substrate. Here, CNT is not in touch with your substrate. So you see, mobility is much higher. Okay, but again, it's very difficult to fabricate such device. You have to etch underneath this CNT to come up with this air between the CNT and the gate contacts. Okay, this is again demonstrated in 2005. This was published in Nature Materials. So again, if you are interested, not only I basically I want to encourage you to scan through these papers, very informative, and you will get better perspective if you go through this paper. These are very interesting papers. Okay. So I hope you should go through all these 4 papers to know more about the carbon nanotubes based FET, right? Because these are fast demonstration of these are different kinds of FET structure of carbon nanotube, right? Now the thing is, so one of the main advantage here is you get much higher mobility out of this structure, so much faster device, simply because, as I said, it is this carbon nanotube is not in touch with the substrate. But the fabrication is really difficult. You need to make trench here, that etching, and make the CNT suspended, which is very difficult to do. Now, if you characterize carbon nanotube based FET, the FET the structure fixed FET IV looks like this. So in other words, it is like it gives both N-type and P-type nature. Okay, it gives you both N-type and P-type nature. The same carbon nanotube FET will give you P-type MOSFET and also N-type MOSFET, right? This particular phenomena is known as ambipolar behavior because it gives you both P-type and N-type nature, right? Now, how does it works? How does it works? To be honest, it works like a Schottky barrier. Okay. I hope you know Schottky barrier, but let me just very briefly mention Schottky barrier. You can get if you deposit metal on top of semiconductor. Usually the contacts are Schottky contacts. If you deposit metal on top of semiconductor, of course that depends of work function and all that of the semiconductor, but primarily it is a Schottky contact if you deposit metal on top of semiconductor. Okay. For example, here you see it is my metal side, it is my N-type silicon side, or N-type semiconductor side, not silicon, N-type semiconductor side. The Fermi level will be aligned. Okay. Now, if you forward bias it, that means if you forward bias a metal semiconductor contacts, you will get electron will this Fermi level will go up and electron will move from this conduction band to the metal. Okay. For example, in Schottky contacts, this is basically something like this. Okay. So in diodes, it is like this. You see, diode, forward bias, reverse bias. In Schottky, you will have like a large reverse bias current. Okay. So it is like ohmic. If you keep on optimizing your Schottky barrier, you will ultimately get a more or less ohmic relationship. Anyway, a ohmic characteristic. But what I want to mean is the metal semiconductor contacts, usually Schottky contacts. It is like metal, and this is N type semiconductor. This is the reverse bias case. But in P type also you can get similar behavior. Okay, why I'm saying this, because the carbon nanotube based FET is basically based on your Schottky technique. Okay, Schottky barrier technique. Now, despite considerable progress in the device fabrication of carbon nanotube, the theoretical understanding remains sort of, I wouldn't say incomplete, remains sort of it's not properly understood. Let's put it this way. Okay, initially it was naturally assumed that the gate voltage modified the nanotube conductor. I mean, in analogy to conventional FET. In conventional FET also, like, gate voltage play the important role. Like, gate voltage will give you the amount of electron or the amount, I mean the amount of carrier in the channel, and you put the voltage between drain and source, that will basically drain out in the carrier, and source will basically source the carrier, right? That is how the conventional FET is. So the gate is important role to play, because gate invert the channels and invert and form the channels, right? So people thought initially like CNT based FET must be work in the same fashion. So gate voltage you apply, you basically modify the conductance of nanotube and so on and so forth. However, there has been increasing evidence that Schottky barriers, okay, at the contacts may play the central role. Okay, Schottky barrier at the contacts play the central role. Okay, in fact, ordinary FETs require ohmic contacts in source and drain. You know, you remember in the ordinary FET, you put n plus here. Okay, and you have like source and drain. These contacts are ohmic contacts, right? Or nearly ohmic. Here in case of CNTFET, these contacts are not ohmic, they are Schottky contacts. So I have carbon nanotube and I have contacts here and here. They are not ohmic contacts, they are Schottky contacts. Okay. So when you apply voltage at the gate, okay, when you apply voltage at the gate here, this depending on the electric field between gate source and gate drain, the band gap or the Schottky barrier will be modified. Okay, so let me repeat it once more. So I have a carbon nanotube, and the carbon nanotube will have like contacts here and here, source and drain, and I have another contacts which is basically gate, right? Now this gate voltage I am applying, and so that this electric field between gate and source and the electric field between gate and drain, they basically modulate or change the Schottky barrier exist at this drain region and at this source region. Okay, so that is the popular belief how it works. So they reducing the width of the Schottky barrier by applying high electric field and allowing thermally assisted tunneling to take place. So if this barrier, if it is very tiny, if it becomes very tiny, then what will happen? The electrons or hole, they basically tunnel the barrier. Okay, so this barrier thickness modification you do by applying voltage at gate and source and drain. That is how it works. That is the popular belief. Okay. So in standard FET, the conductance is controlled by electrostatic potential, as you know, okay, in the channel by applying voltage at the gate. But here it is not the case. It is basically, in contrast, what you do, you use SB FET, that is Schottky barrier FET. The performance largely controlled by the electric field at the contacts, right? I've tried to draw this band diagram. So you see valence band, conduction band. Okay, so depending on what kind of voltage you are applying, okay, you can have like P type the FET, or you can have like N type FET, right? So here you see holes are flowing through the valence band, okay, reaching to the drain, And here you see electrons are flowing through the conduction band. So you see, depending on how you are applying your voltage, okay, both at the gate and also at the between drain and source, you basically thinning down or changing the barrier, Schottky barrier. Okay, that helps to tunnel the holes or tunnel the electrons, and you get current, right? And you will get both p-type and n-type nature from the same FET, and this is known as ambipolar FET, right? What else? So we have another 20 minutes or so. So I thought that I will talk about bit of graphene, because graphene is very interesting and graphene is very lucrative. Okay, although graphene was developed much later than carbon nanotube. Although I showed you that I showed you at the first slide that if you can roll this graphene sheet, you can get carbon nanotube. But the thing is, graphene was discovered much later than carbon nanotube, because we don't make carbon nanotube just by rolling by hand, right? You see, we use arc discharge technique or the laser ablation technique or CVD or PECVD. So many different techniques are there. So it is not like physical rolling. So in other words, graphene was demonstrated much later than carbon nanotube. Graphene was demonstrated beginning of 2000. Okay. And it was demonstrated by in University of Manchester. Okay, so let me go back to that slide. University of Manchester by Andre Geum and Professor Novoselov. Let me just go to that slide here. Okay, so Andre Geum and Professor Novoselov, I think around beginning of 2000, and so they got Nobel Prize in 2010. So you see, for CNT, Ijima didn't get Nobel Prize because there was controversy whether Ijima discovered it or it was discovered much before Ijima discovered the carbon nanotube. So there were this debate, but with this, graphene there was no debate. It was first demonstrated in University of Manchester using mechanical exfoliation technique. Okay, using mechanical exfoliation technique. These Andre Geum and Professor Novoselov, they first demonstrated graphene, that is single layer of graphite. Okay, as I said, it is also sp2 hybridized honeycomb structure. Okay, and there are different ways to fabricate graphene also. The different ways. Now today, what I am planning to do, I will run a video. I don't know you will be able to. I don't know it will run or not, but let me try. I will run the video from University of Manchester group, that's from the same group, and University of Cambridge group, because those two are very strong group who did a lot of work using graphene, just to show you how graphene first time was demonstrated. Okay, so if the voice doesn't work, then I think you have to listen to my voice. Okay, so let me. I just want to switch off the video because I mean I want to switch off the recording. Sorry, because it is a YouTube video. I just don't want to. Please don't record this. If you want, you can start.